Hey, and welcome to a functions video. This video is going to be particularly great because it gives me the excuse to pretend that I actually make functions videos. So, let's take a look at this function. We have f of x equals x to the fourth plus 5x cubed minus 25x squared minus 5x plus 24 all over x cubed minus x squared minus 6x. This kind of function is in the family of rational functions because it has one size function on the top and something else on the bottom, and it divides them. So properties of a rational function include that it can have vertical, horizontal, or oblique asymptotes as well as wholes. So let's move on to the first little bit of our function. So this is really a bit of a monster to look at. You have a fourth level equation on the top and a third level equation on the bottom, neither of which are particularly nice to work with. Well, good news is it gets easier. Let's break it down. Alright, so we know our last term here is 24. This will be what we use with the factor theorem over here to help us factor this equation into some simple factors which will make it much easier to work with. So, the last value here is 24. So let's look at factors of 24. You have 1 and 24, 2 and 12, 3 and 8, and 4 and 6. Now I know some things you don't, and I also like the number 8, so we're going to start with 8. Is x plus 8 a factor? Well, let's find out. So you do long division, divide, subtract, multiply, bring down, blah 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 blah, same thing over and over and over. Okay, here we are. We have no remainder, we have x plus 8 as a factor, and what we're left with is a cubic. X to the third minus x squared minus x plus 3. Well, let's do long division again. This time we can be pretty sure x plus 1 is a factor. It seems kind of right, you know? So let's go on here. So, we end up no remainder. That means great. X plus 1 is a factor. We're left with a quadratic equation, x squared minus 4x plus 3. You can factor this whatever way you like, but either way you're going to end up with the same factors, x minus 1, x minus 3. And then let's look at the bottom of this rational function, the denominator. This is a cubic. Conveniently, all these terms contain x, so we can divide x out of each one. This means x is a factor, or x plus 0. What we're left with is again a quadratic. We can factor this into x plus 2, x minus 3. Great. So now we can look at our final rational function with everything in factors, and we have x minus 3 times x plus 1 times x minus 1 times x plus 8 all over x times x plus 3 times x plus 2. That is a much nicer equation to work with, and these factors that we see right here will give us the properties we'll look at on the next slide here, which is a graph. This is the graph of the big ugly function we just looked at, which you can see up here. F of x is x to the fourth plus 5x cubed, blah blah blah. We don't really like that. Let's just use the factored form from last slide. Well, what do we know from the last slide? We know some of what our equation is going to look like. We know it's got no horizontal or vertical stretch based on the fact that there's no a or k value. We know it's going to have an oblique asymptote because the top is 1 degree higher than the bottom, and we know it should have vertical asymptotes because of what's on the bottom of the equation as well. Now, let's take a look at this graph in some more detail. So here are some key points. We have a hole here at point 3 and undefined because it's a hole. This is caused by dividing out of a factor that's in the numerator and the denominator, which we'll look at on the next slide. We have a vertical asymptote right on the y-axis here, which is x equals 0. That also means we'll have no y-intercept. We have another vertical asymptote over here at x equals negative 2. That's thanks to the denominator, and we'll look at that later on. This oblique asymptote, we'll have a slide we'll look at that and see how it gets to be there. And of course we have an inflection point, so that's where the slope's coming up, and it comes in, and the IROC of that point reaches 0. And then it flips back up and starts accelerating faster. And we'll take a look at how that gets there as well. So let's move on. So here are some key points and features. Roots. These are super useful things which you could look at if you zoom in on the graph in the last slide. So the roots are found when the f of x is equal to 0. So we end up with our whole equation. If you look at the top, we have an x minus 3 on the top and 1 on the bottom. Those cross out, and those will form a whole, which we see is marked by this on the graph, which we saw just a slide ago. Now what we're left with is x minus 1, x plus 1, x plus 8, all over x times x plus 2 equaling 0, and we find our roots. Now, the denominator really doesn't matter here, because we're going to multiply both sides by that. Left side times the denominator is this numerator right here, and right side times the denominator is still 0. So all we're looking at here is the numerator. So we end up with x minus 1, x plus 1, and x plus 8 equals 0, which we can simplify to x equals 1, x equals negative 1, and x equals negative 8. Those are our roots. So key points on the graph, that'll be negative 8, 0, negative 1, 0, and 1, 0. Now the inflection point on this graph we found graphically using a table of values. So if you were to look, you'd see that the slope comes up and up and up and then starts decreasing and decreasing, and it approaches 0. Then finally that slope reaches a steady point, stops, and starts going back up. So that moment where the slope would reach 0 is the inflection point, and that was just solved using a table of values, as you saw on the graph. Asymptotes. These are everyone's favorite part of a function because they aren't actually a part of the function. So we get our vertical asymptotes from the basic fact that you can't divide by 0. So you have x plus a is n equal to 0. So if we have here, we have x and x plus 2, we can't have those equal 0, so we know that's really x plus 0 and x plus 2. So we know x can't equal 0 because 0 plus 0 is 0, and x can't be negative 2 because 2 plus negative 2 is equal to 0. So we say x is unequal to 0 and negative 2, therefore our vertical asymptotes are at 0 and negative 2. Let's look at this oblique asymptote and how we got there. So we have what's left of this function once we've cancelled out what needs cancelling out. X minus 1, x plus 1, x plus 8, all over x times x plus 2. We'll expand and simplify the top and the bottom. We end up with x cubed plus 8x squared minus x minus 8 over x squared plus 2x. You perform long division, and you find here you have a remainder, negative 13x minus 8, but what you have is, as your end product here, you have x plus 6. So that's your oblique asymptote, y equals x plus 6. So this is an asymptote because what you have is negative 13x minus 8 over x squared plus 2x up here, and then that's being taken away from or added to, depending on which side you're on, of this oblique asymptote. So you'll never quite reach it, but it'll get infinitely closer to that line, y equals x plus 6. So this function has some basic characteristics which will be nice to discuss. There's the domain. It's a nice, simple domain. D equals x is a member of the real family such that x can't equal negative 2 or 0 because of asymptotes, or 3 because of that whole. The range is much more straightforward. R equals f of x is a member of the real family. Simple. Now because we have asymptotes and a whole, our function is obviously discontinuous. Our end behaviors are fairly straightforward as well. As x approaches infinity, y approaches infinity, as we saw on the graph, and as x approaches negative infinity, y approaches negative infinity. This function is always increasing except where the asymptotes are. So it increases on the interval x is less than negative 2, negative 2 is less than x is less than 0, and x is greater than 0. There's no symmetry in this function, even or odd. So due to vertical translations, f of x is unequal to f of y, and f of x is unequal to negative f of negative x. Therefore, there is no symmetry to be found in this function. Let's move on to the next section, the instantaneous rate of change. Now, this is the last section of this little video, the last slide here. The instantaneous rate of change on this function will only ever be positive because the function is always increasing. So let's look at how we can find an example of this positive instantaneous rate of change. So we know f of x plus a minus f of x all over a is equal to the instantaneous rate of change, or tangent. We'll set a equal to 0.001 because that's a nice small number, and pick x equals 4 because 4 is a great number. So we have f of 4.001 plus f of 4 all divided by 0.001, which ends up working out, when you do all the math, to be 7.5015 plus 7.5 all over 0.001, which you simplify down, you end up with 1.5. So the instantaneous rate of change at x equals 4 is 1.5. Now, I can't really put that 1.5 in a unit. I guess I'd just say x per y, because this function really has no practical application. If we take another look at the graph here, it's really not a particularly pretty function. Doesn't do anything useful, doesn't model anything, but hey, it's a great function for this video, and again, an excuse for me to pretend like I know math things.